We got another example here. For this one, we've got water in a piston cylinder assembly. Initially, the pressure is 10 psi. Our temperature is 500 degrees Fahrenheit. It's going to undergo an internally reversible process where we get a final pressure of 80 psi and temperature of 800 degrees Fahrenheit. And it tells us the temperature is going to vary linearly with entropy. Now we want to determine work and heat transfer in BTU per pound. And we're going to neglect kinetic and potential energy effects. Alright, so pay attention to where it says this varies linearly with entropy. That means if we could write an equation for temperature, we would have temperature equals some function of S. Alright, so we'd have an equation like that. We don't know what the equation is though, but we just know it varies linearly. Now, we want to find work and heat transfer. We want it to be BTU per pound. This per pound part is going to be important. Now for Q, we finally have another equation besides the energy balance equations for Q. This one we can write as Q equals the integral from state 1 to 2 of TdS, where S is capital, and that is going to be our equation that we'll use for Q. Now, T is some linear function of entropy. We don't know what that is though. Right, so we don't know the actual equation. So if we go through and integrate this, what we're going to do is we're just going to use the average temperature. And that'll be good enough because it says it varies linearly with entropy. So this will just kind of be an approximation. This says AVG. I know it's hard to read there. And then we'll have S2 minus S1. If we would have been given the actual function, we would have plugged that in here and then done the actual integral. Since we weren't, let's just do an estimate, use the average temperature. Now we need to get these S values. All right. So we'll have that, and for that you have to go to the tables. So let's head on over to the tables. Let's look at S2 and then we'll look at S1. And if we do that, first let's start with the saturated water table. Initially our pressure is 10 psi and our temperature is 500. Alright, so here is 10. Saturation temperature is 193.19. Our temperature is 500, so what does that tell us? We need to go to a different table. That's what that tells us. So we need to go to the superheated vapor table. And let's just go ahead and check the second condition. We're going to a pressure of 80. And you can probably guess. So 80, our saturation temperature is 312. We're at a temperature of 800, so obviously same table. So now we go to table A4E. Let's write that down. So table A4E. And then we're going to look up our properties. So we have pressure of 10. So here are our superheated water. Pressure is 10. We are at a temperature of 500. We want S. That's over here. So 1.969 is what we get. That was for our initial one, so we'll put that right here. Units, BTU per pound degree Rankine. Then we do the same thing for the second state. I wrote these backwards, but that's okay. Second state, we have 80 psi, temperature is 800. So now, come over here, here's 80, we're at 800. We need 1.87. So now we got 1.87 BTU per pound degree Rankine. All right, so far so good. Remember, this is specific entropy. All right, because that's what's in the table. So make sure you pay attention to that. Now, let's go ahead and get our equations. We want BTU per pound. That's the unit we want in our answer. Here's our equation we're going to use. This equation is just going to give you BTU for the units at the end. We want BTU per pound. So why don't we rewrite this as Q over M and then have that be our average temperature. So we're going to convert our temperatures, the 500 and the 800, those need to go to Rankine. So you convert the 500, you'll get 959.67. All right, so that's for the 500 Fahrenheit. And then we're doing an average here, so let's add the second temperature. So it's 800 Fahrenheit. We need to convert that to Rankine. That's 1259.67. So that's for the 800 degrees. And let's divide that by 2. So that'll give us a good enough estimate for the temperature, going from state 1 to state 2, since it's going to vary linearly. All right, so now we've got that. Now we need to do S2 minus S1. Now this equation has regular entropy. We have specific entropy. Well, let's go ahead and write down what we have. 1.87 BTU per pound degree Rankine minus 1.969 BTU per pound degree Rankine. Now if you look at our units, we've got Rankine in all of these, so they cancels out. That's going to leave us with BTU per pound, which that's what we wanted. Okay, so if you use specific entropy here when you do the difference in S, what you get is Q over M, and that's what we were wanting because we want BTU per pound. All right, and we had to do it that way because we don't know the mass, so we had no way of converting these to regular entropy, right? So there you go. Quick workaround there when you don't have the mass. Now Q over M is going to be negative 109.857 BTU per pound. All right, so there we have that. Now let's go ahead and we want to find work. Now for work, what we're going to do is we'll use our energy balance equation. That's going to be the easiest thing to do here. Remember, this is a closed system, so the equation you have for a closed system, you're going to have delta U plus delta KE plus delta PE equals Q minus W. Now we're going to neglect those two, so those go away. And remember, this is only to be used for closed systems. We have a closed system though, so we can use that. Now this is internal energy, not specific internal energy. So this is really M times U2 minus U1, which equals Q minus W. Now we want W over M since we want BTU over pounds. Let's divide through by M. It's going to give us U2 minus U1 equals Q over M minus W over M. All right, so we already got this, right? And these two you can find in the table. So, easy. Not too much more to do. U2, you're going to go to that same table we went to before, so A4E. That'll give you 1292.4 BTU per pound. And then U1, you'll be at 1182.2 BTU per pound. Now all we have left to do is plug everything into this equation. So we'll have 1292.4 minus 1182.4. Those are BTU per pound. That's going to equal Q over M. Let's move that where you can actually see it. So we'll have negative 109.857 for Q over M minus work per mass. And I didn't write the units, but this is BTU per pound. Now you can solve for the unknown. All right, so work per mass is going to be negative 220.057 BTU per pound. This is negative, so since it's negative, you would have work coming in to your system. Now if we look at the sign for Q, this one's negative, so this means we've got energy transfer by heat going out. Because remember, they're kind of opposite. So if work is negative, it's coming in. If Q is negative, it's going out. Okay, so we're gaining energy here, losing energy there. All right, guys, so that's kind of how you can use entropy to determine heat transfer and work. Hopefully you like that example. I will see you guys in the next video.